Hello, everyone, and welcome once again to the TBS colloquium series. Today, for the first colloquium of this year, 2025, we have Łukasz Wyrzykowski. I knew I was not going to do that right, but he's a professor in the University of Warsaw, and he's also the PI of BHTOM, and he will tell us everything about that now. And so, please, Łukasz, take it away.
Okay, thank you very much. Thank you for the opportunity to speak to you at being the first in this year. So I hope I can, with my talk, I can distract you from all the difficulties and difficult topics which are going on out there. So let's focus on what we love most, and I hope this talk will encourage you to think about science and potential future collaborations as well. My name is very difficult. So Łukasz is fine, and Wyrzykowski is my surname. It's a very difficult Polish name, and I'm a professor of astronomy at the University of Warsaw and National Center for Nuclear Research. And I've been running this telescope network for actually now something like 12 years now. But I also been doing a lot of time domain science in the past. Partially also already starting within the LSST TVS collaboration. So maybe with some of you we have already overlapped and met on some occasions. Okay, so the topic of the seminar here today is to present you the BHTOM. You will find out what it is, and also to present you. Actually, it's the first time I'm giving a public talk about the European Astronomical Society of Small Telescopes. So more about this later. Okay, so this is the background of the slide, actually, of my title slide, where you see the map, but we'll get there in a second where we are. But this is a global initiative. That's what I wanted to emphasize here. But before I continue, I wanted to show some faces of people who are involved in this. These days, you don't do things alone, of course. So these are the people mostly located in Poland, but this is an international group. Some people are located at the Warsaw University. The other part is NCBJ, and I'm actually now looking for postdoc and software engineer for this project. So if you know of anyone or you're interested, there is still possibility to join the team. So I hope maybe some of you will get encouraged. But also this work has been overlapping with many other projects, primarily with Gaia and European Space Agency DPAC consortium around Gaia, but also we collaborate with PESTO, EPESTO, ENGRAVE, OGLE project, Las Cumbres Observatory, and of course LSST. And there are more partners involved here and people from all around different places. Okay, so I will be talking mostly about, I will start with talking about Gaia to give you the context, because I think this is a spectacular mission, or maybe I should now be saying was. And I've been involved in Gaia from essentially from its very beginning. I joined the collaboration in 2008, way before it was launched. But let's use Gaia here as an example of a survey. This is just a time domain optical survey. You can think about LSST as yet another generation optical survey of large portion of the sky. Where we are now, we're trying to, all the lessons learned with Gaia, we're trying to transfer. We might be able to transfer some of it to LSST environment, but also you can think about ZTF, you can think about ASASSN, Atlas, every other survey you have in mind, not only optical, but also thinking multi-wavelength, multi-messenger, all this applies as well. But talking about Gaia will give you my kind of historic perspective as well on this and how it all developed. So speaking about Gaia, so this is an ESA, the European Space Agency mission. It was launched in 2013, and actually it stopped its scientific operation not so long ago, on the 15th of January 2025. And now it's in the process of technical tests before it will be kicked out of the L2 location to leave space for future missions, which because it's getting quite busy in L2. It's a 10-meter spacecraft wide. It looks like a flying saucer actually, and it has two 1.4 meters. So it's fairly big as for space mission. And it goes down to 20.5 magnitude, and it monitors 2 billion sources. And essentially it doesn't have a particular goal except for collecting photometry, astrometry, and spectroscopy for all these sources. However, its primary methodology, what you can do with it, and why Gaia was built, is the trigonometric parallaxes. And you see on the right, this is how the trigonometric parallax looks like, where Gaia is located in L2 in a heliocentric orbit around together with the Earth, where Gaia is observing the stars, and they appear to move. So essentially, by measuring motion of stars, this is what Gaia does to superb accuracy. Gaia is able to measure parallaxes, distances to stars, as well as velocities, proper motions, and many other properties of stars. And Gaia data releases were published in the most recent one was in June 2022, and the forthcoming one, DR4, will come in around mid-2026, and it will contain all data from the very first 5 years of the mission. Just to show you an animation, how it looks, as I said, it's a flying saucer, and it spins around. The spin period is exactly 6 hours, and then the spin axis precesses. This allows Gaia to observe the whole sky with the two mirrors fairly quickly. Gaia is able to monitor the entire sky multiple times. As you see on this animation, this is the way Gaia scans. Typically, the field of view is 0.7 square degree per observation, but Gaia is scanning all the time. So you can imagine this 0.7 degree wide stripe across the sky, and then it's then repeated and observed again. Typically, there is something like 200 up to 200 epochs per observation. With every object being observed good couple hundred of times. And the main thing is that Gaia is observing the whole sky, essentially the galactic disk, the galactic bulge, galactic halo, and outside of it. It's primarily galactic mission, just to keep that in mind, but not only. Of course, it observes every object. It's not biased, so there is 3 million quasars published within Gaia catalog, and good tens of millions of galaxies with their properties, time series, and so on. My particular scientific interest, I'm going to talk about a little bit more here, is the gravitational microlensing. However, you can again think about it as an example of a time domain problem. Essentially, you have time series observations of stars. This could be also as well supernovae. Supernovae are transient, but also they're essentially time domain objects. Variable stars are time domain objects. Varying quasars are time domain objects. Gravitational wave optical counterparts, these are time domain objects. So I've been working on microlensing events, especially within something what was called Gaia Science Alerts, and this was done with the collaboration of the University of Cambridge. And this is the website where we've been posting the alerts from the very beginning of the mission. So not even waiting for Gaia data releases. Starting from mid-2014, when Gaia was collecting first scientific data, we started alerting on things that change on the sky. You think again of supernovae, CVs, but also we've been alerting on stars changing their brightness, going up, going down, disappearing, reappearing again. Everything was a potential alert, what was worth alerting early on, and then Gaia is moving on in its scanning, but the ground was informed, and so we could continue the studies of these objects from the ground. So this is an example of a microlensing event alert. So essentially you have a star which has been doing nothing for many, many years, and then suddenly it goes up significantly. This one is got the name Gaia 2022 BPL, and we like to call it Bogdan Paczynski lens because he was the founder of the microlensing idea in general. But the name's actually, the BPL, it was just a random, let's say a number encoded in letters. And typically we've been finding like 1 to 5 new events every week in real time. These are rare events, I just want to mention. 1 in a million stars gets lensed, but because of Gaia volume Gaia was probing, we've been finding quite a lot of a large number of these events. This is one of the first examples we found, Gaia 16 AYE. This turns out to be one of the most complex microlensing events, but it was not a black hole. Of course, we're looking for black holes because this is fun. This is where fun is, and with microlensing you can find objects you don't see, the lenses themselves. They can be black holes or planets. So this one turned out to be a binary system, very faint and invisible, but it was causing the lensing system very, very complex. And you see what was crucial here, after the alert, we alerted dozens of telescopes on the ground, excuse me, and we asked them for the observations of that particular target. And we had a tremendous response, and we collected 20,000 ground-based observations from 50 observatories. And only thanks to that, we've been able to reproduce the event itself. Otherwise, with Gaia data alone, it would just look like some crazy, weird variable star. While all the observations from the ground, they allowed us to trace these rapid changes and very sudden changes in the behavior, the photometric behavior of the object. In multiple filters as well, as you see different levels, they show different filters. So we had multiple caustic crossings here, we had a caustic approach, we had small bumps, big bumps, and so on. And only thanks to this follow-up effort, note that this lasted more than a year, right? So no telescope would give you so much amount of time for 1 year to get such a dense data. And some changes were happening within a couple of hours. So only thanks to that, we were able to build the model, a very complex model of the rotating binary. So the binary was rotating while lensing, right? So the source was passing by in the background, and the binary lens was in front and was rotating, and it was lensing and also changing the projected separation. So that's why we call this one as probably the most complex microlensing event ever. Moreover, what we did in Gaia, and this is something what is very important for microlensing, but not only microlensing, is that Gaia collects photometry, but also astrometry. So these superb astrometric measurements Gaia uses for parallactic measurements and so on, they are also available for sources which are doing different things. And microlensing causes not only things to get brighter, but it also shifts things on the sky. And I'm going to play this animation here to show you what has been happening during that event to the location of the source we observed. So you can follow the right hand side animation, because this is on sky trajectory, where you will see the dashed blue line is the actual trajectory of the source, while the red one is what we see. Right, so this is the distorted position of the source when it was lensed, and lensing by this crazy caustic makes the source jump around all over the place. So let me play this. So you see there are two lenses there, and they are rotating, and the binary system is causing this system of caustics. So we haven't reached the caustics yet, but here comes the source. And because the lens is nearby, the observed location is already displaced. And now we hit the caustic. You see the source jumps from all over the place. So this is the actual on-sky measurements from Gaia we were able to use for that event. Because we solved the event before, we were able to understand the positional measurements from Gaia. Even the tiny caustic at the very end, we were able to catch it in the photometric data. Anyway, this is just to show you the powerfulness of Gaia data, that there is not only photometry, but also astrometry, which is crucial. And this is going to be released in Gaia DR4. Especially for microlensing, this is crucial because this allows us to measure the masses of lenses and find black holes among the lensed events. However, here I want to focus, of course, on the follow-up. This is another event we found. This one was extremely long, so it lasted many years. There was not enough follow-up here, so hence we have a very poor coverage. And this is this acts like a counterexample. If we don't get a good follow-up in time for these kind of events, then even if we get superb Gaia astrometry, in this case, it will be also difficult because this one is very faint, then we lost the scientific case, meaning that we could have detected a black hole lens, especially in long events. This is more likely to have a black hole lens, but we essentially missed it because our cadence was way too low, and we were not able to disentangle different scenarios here. Here we have a candidate for a massive object, well, something like 2 solar masses or above, and we did not detect any light from the lens itself. So we think this could have been a neutron star or maybe even a black hole, but our error on the mass is extremely huge. So this is just to emphasize the importance of the follow-up. Yet another example of a binary event. This is not as complex as Gaia 16 AYE, but again, this one was observed very densely. And after Gaia alert very early on in the light curve, we were able to trace the entire, this funny U-shaped caustic, especially the very edge you see here, where the source was getting brighter and then suddenly dropped in brightness by well, something like 1 or 1.5 magnitudes within a time frame of like 5 hours. So for that you need 24 hours monitoring from multiple places on the ground, essentially, or you need a space observatory, of course. But so far we don't have these, so we have to rely on this. So only thanks to the follow-up, we were able to find the model and essentially solve the event, and they do not repeat. I repeat that these events do not repeat. They are so rare that they happen once in a lifetime and then they go away. So again, as I said, use this exercise to think about other science cases which are more relevant for you, where you need dense and what from dense light curves, what else, how important information you can extract. Yet another example, here we found a white dwarf, possibly only again thanks to the follow-up. Here we actually had a space observations, not only from Gaia but also from Spitzer. But this is just an additional caveat to that event. But the ground observations were crucial. And the last example here, again, a faint event where we didn't get the follow-up because we were not ready back in 2018 for this event. But here we think this is 12 solar mass black hole at 2 kiloparsecs away. And here we also published some, this was published by my student recently, together with the code for studying these events. So this is just to advertise the work I've been doing. So now let's move on to the telescope network. So we call it BHTOM telescope network. It used to have different names in the past. It was related with Gaia alerts. It started actually back in 2013 when we were about to launch Gaia. And then it has been growing. So at this very moment, we have about 120 telescopes which are associated with us. And this is the map from around the globe. The sizes go from 0.25 to 2.5 meters. And these are professional instruments. These are also amateur instruments. These days, amateurs, very often, they have telescopes and instruments which are far better than the old instruments some of the professionals have. It's much easier to work with these new telescopes. They are essentially robot ready. You can plug them in and essentially get science out of them. But on the other hand, you need to help the amateurs quite a lot, significantly. Tell them what to observe, tell them how to observe, what kind of data is good, what kind of data is not good. Essentially, the knowledge professionals have. So this is what I want to emphasize here, that this is what we've been doing actually for the last 12 years. We also have schools. Schools build observatories, and these observatories are being used for school curriculum. But then very often in the evening they're shut down, they're closed because the kids don't go there. So the telescopes can do the job, do the robotic observations while the kids are asleep, and then the next morning they can go and see, oh, look guys, this is the supernova which was just observed last night with our own telescope. So if you have a creative teacher, they can take it away from this and make a very inspiring class about the expansion of the universe or whatever you can think of. And of course, you see there is a huge concentration of these telescopes around Europe. This is kind of, this gives the bias I had from the very beginning. This is a zoom in around Europe, but this is actually, this is what it is representing, that there has been many institutes, scientific institutes, astronomical institutes established over the last 100 years, way before the superb observatories has been established, like Hawaii or Chile or even Australia. So these telescopes are still there. They're mostly used for educational purposes, but not always. So and they are, you see the map is showing the cloud cover. So in Poland, the weather is really, really poor. However, if you have many poor weather telescopes combined together, you end up having a clear sky somewhere, right? We've had cases where the telescopes we've been hoping for in Spain, they were completely clouded out, while the weather in Poland and Lithuania was much, much better. So we collected the crucial data from north of Europe instead of south of Europe, right? So you cannot count on weather all the time. So you have to have telescopes everywhere. And also it gives you, of course, the natural longitudinal coverage. And then the latitudinal coverage also helps you with some targets which are more difficult to observe from different hemispheres. Okay, so BHTOM, it's actually a shortcut, it's an acronym from Black Hole Target and Observation Manager. Black hole because it sounds nice and interesting. It catches people's attention, I hope. And TOM is the name we've used after TOM Toolkit, which is LCO, Target and Observation Manager. So this is to acknowledge the tremendous job done by LCO, where they essentially, all the experience they gathered within LCO network, they shared with all the people, and they made the TOM system available open sourced. So I was lucky enough to spend some time at LCO, and I got some first hands-on training on TOMs, building TOMs and using them. And then me and my team, we accommodated it to our network. So we still very closely collaborate with LCO and TOM people. So this is still an ongoing adventure, but this is just to acknowledge that it wouldn't have happened if it wasn't the LCO TOM Toolkit. So essentially this is a web tool for coordination for time domain observations. It handles the automated observation requests. It processes raw images from heterogeneous units. This is what differs us at this moment from a typical TOM. And then also what we do, we standardize the data automatically. We also query all possible archives, multi-wavelength archives for time domain photometry. There's many catalogs out there which are available. But most of them are like static. Even if they were collecting data multiple times, then they stack it. They want to reach as deep as possible. What we are interested in is the time domain history, because then you can learn a lot about objects of interest. And of course, the advert here, we are open for new users, new telescopes, new targets. We are currently running Black Hole TOM 2, but we're already thinking about Black Hole TOM 3. I'll tell you about this in a second. So how does it work? This is a kind of a schema of operation which you kind of can feel familiar with, because this is nothing original, to be honest. But this is, I'm going to show how we fit in the entire environment of transient and time domain science. So there are these surveys, right? And I showed an example of Gaia, but you can think of anything else: ZTF, LSST, IceCube with neutrinos, GW triggers, and so on. They produce alerts. So these alerts go to brokers. I'm sure you're all familiar with brokers. I just give a handful of examples here. So the brokers are there, and they're doing tremendous work to help users to find what they are interested in. And the users can ask different questions, right? So someone can say, okay, so we found these 10 candidates for gravitational wave optical counterparts. The other user can say, I want this object to be observed for 1 year, all the time, as frequently as possible. So these are kinds of requests you can think of, and these observing requests, they go to BHTOM.space. And what we do with them, we essentially communicate with the network of telescopes. And the way of communication, it depends. As I said, some of the telescopes are completely manual, operated by very old-fashioned telescopes. Some of them are completely robotic. Some of them are run by amateurs. Some of them are run by schools. But we are, again, working with LCO people on the EON protocol, so Astronomical Event Observatory Network, which is a protocol which allows for automated communication between telescopes and TOMs in general. So our TOM is also within. We're trying to make this connection feasible with our telescopes. Another piece of software which is made available by LCO is the Observatory Control System, and we do encourage strongly, and we collaborate with people from our network to install the observatory OCS on their telescopes, because that makes things much easier to talk with them, not only one way, but also the other way around, right? So they receive a request, and then they can send us the data, and this is all established within well-defined framework. We don't have to reinvent the wheel. Sometimes the EON for some of the telescopes is essentially an email, and we do that. We send an email, automated email, to the telescopes saying, look, these are the targets which are now of interest. So please observe them, put them into your scheduler. And this is on their side, they add them to schedulers. And then once the data is collected, we get the data back into our system. What else we do? As I said, we access the archives, but with a particular focus to time domain archives. I will show some examples later. And what we give back to the users is essentially the science-ready data products, right? So you see, we try to shield the users from sending their observing request to multiple telescopes. Like, this is the most classical way. You apply for time. You have to apply for time on multiple telescopes if you want to do time domain data like this. But you don't have to do that. You just go to one place, to us. You don't have to write any proposal. You don't have to buy any time. It's all free. You just have to register and put your target in, and we will observe it for you, right? Moreover, you don't have to worry, how do I process the data from that obscure telescope somewhere there in Poland? We do that for you. And all the data from all these different units, different heterogeneous telescopes, are homogenized and standardized. And this is what you get as a user for your science. And essentially, all you have to do is to write a paper with the data collected here. Of course, in these days, everything can be scripted and automatized. So all this data flow I showed you here can essentially get rid of humans. It's possible in some cases. It's difficult in others. We're trying to make it as smooth as possible. But TOMs, LCO TOMs in general, from the very beginning, they were meant to be operated by robots. So this is there. This is the inherited the feature of the TOMs, and we are also trying to use this in our system. Just to show you more examples here, these are the telescopes we have collaborating with us, different apertures, different locations, different operating modes. And again, this is a light curve, example light curve of some crazy weird object we observed. And on the right, I show that we keep track of every data point, who collected it, with which telescope. We can then clearly see what kind of data this person has collected and how much, and then provide some statistic afterwards, and then also include people in the papers. We know who contributed where. And speaking of which, I wanted to show you an example of one of our partners, which is actually a school observatory. So sorry for everything being in Polish, but this is a Polish observatory located in the mountains. And they managed to observe not only transient targets and time domain objects, but they managed to observe just a week ago, they managed to catch Gaia itself. So I'll start the animation here. So this is, 1.5 million kilometers away. And you see this object is moving. So it's played a couple of times, but I hope you can see the object being very bright and moving. And this is a video caught by the camera inside the dome of this robotized school observatory while they were observing Gaia. So this is a full robot which has a scheduler and it is reacting to sky coverage, cloudiness, and weather changes. So this is an example of an observatory. They've been collaborating with us for quite some time already. As I mentioned, so we process the data, and this is probably our biggest difference and biggest contribution to the community, I think, because we can then accept data from multiple telescopes. You see example observations here from different telescopes of different targets. And then what we do, once we measure the PSF photometry, we standardize it, and we even detect the filters automatically. So you can just dump all the images you've collected. We typically don't trust headers. That's our experience. The headers you should not trust, and whichever filter it says it's in the header, we double check it with essentially matching it with the Gaia synthetic photometry catalog. This is a unified, homogeneous, all sky, homogeneous multi-filter catalog, which we now rely on and standardize the observations too. So here we detected that some observations were taken in Sloan I-band observations. And this allows us to standardize the observations from all these observatories to one system. As I said, everything is programmable. So there is an API. Essentially, all functionalities are accessible via API. And we provide scripts for data flow to and from telescopes. So essentially, you don't need to use our web page at all. You can just use a script which uploads the data and downloads the photometry. All the observing requests, everything can be automatized and scripted from your side. We work with Astrocolibri. That's a similar platform for multi-messenger observations, and they are already using it. They have a button, submit event to BHTOM, and then they grab the data from us. And as I said, we provide the scripts for this. Some statistics. At the moment, we have 448 users, but it keeps growing, 3 new users every week. Currently, we have 300 targets requested for observations. I know these numbers are kind of small, but I'm sure we can handle more. Essentially, this is what's going on the sky now, and we're trying to reach out to other scientific communities as well to have more and more science cases present in our system. In total, we have something like 4,000 targets, historical ones now. So they've been observed, now they are not of interest. So the database is growing. We've processed so far 220,000 images. They were uploaded automatically. This is the statistics on the right showing you that there is one particular observatory which is very, very active. It's an amateur observatory actually located in Chile, so it has very good weather, and it's a full robotic observatory. So that's why it can devote a lot of time to the observations we request. So 33% comes from that. LCO has also contributed quite a lot, but also, as you see, 50% of our observations come from more than 80 observatories, right? So if it was just road and LCO, we would have had only half of the data we have at the moment. So some people are contributing maybe a few observations every night, but some of them are contributing hundreds of observations per night, right? And we don't require them to devote themselves a lot. We only ask them to observe whenever they can. So some telescopes are running their own programs, but we often go as a filler program, right? Because we always have a target of interest. So if you're looking for you have a telescope and you're looking for some filler program, this is where you can take the targets from, because most of our targets, they require very long time observations. That's why there is always something what you can contribute to. You contribute a couple of points now, then you contribute a couple of points next time, and then other people contribute in between, and essentially that way we build a light curve. Yeah, so we process something like 10,000 images every week. And of course, as I said, we invite new telescopes and new users. Here are some statistics of the number of observations processed every week, and it has been growing. We essentially started at the beginning of 2021, and we've been having workshops as well, organizing workshops to keep this community talking to each other and also encouraging people to join. And there are some correlations between the spikes in this chart with the meetings we've had. And we tend to have them in nice places like Crete, Sardinia, or Salerno. More about workshops later. Just to show you some other science cases and we have in our system, so that this is not only microlensing, of course. So cataclysmic variables, it's a big chunk of our scientific interests. So you actually see the light curve with both current observations and archival observations from multiple observatories and surveys. So the data spans here nearly 20 years. Here is a quasar. There's a flaring quasar detected by Gaia, and there is some ZTF observations. There's Gaia data. There is NEO-WISE data here loaded automatically, but also this object was observed by SDSS long time ago, and PanSTARRS, and DES as well. There are some AGNs which are worth studying by people in terms of photometry. So you can actually type in the coordinates, you can get all the archival data for the object. And some people are actually using the BHTOM solely for the ease of accessing the archival data. Some other examples. Another AGN, just to show you that we also grab the radio information, radio observations, radio time series are also being queried. And this is a supernova, famous supernova 23XF. So we've collected a lot of data from essentially from all bands. We even we started working. It's almost there. We can add Swift observations, process Swift data, and add it to our photometric time series if the object was observed multiple times with Swift. So this is Swift data added to this object. We found a planetary system using microlensing. You see this tiny blip here on top of this light curve, so seen in multiple filters. So this is a data. This is a light curve. You see how smooth it is, and these data points, they come from multiple observatories. So you actually sometimes cannot tell that there are different observatories involved. More examples. This is some crazy eruptive variable which is varying on timescales of days or even hours. So we have quite a lot of observations of these. Another supernova, 24 GGI, a beautiful light curve collected with multiple observatories. And again, long, crazy binary microlensing event. Just to show you last example, how the follow-up is important, to something what I started with. And this is the Gaia 20 FNR alert found by Gaia around this time here in November, December 2020. So this is only Gaia data. You see, the data comes more or less every 30 to 60 days, right? This is a very sparse cadence for many science cases. And this is the ZTF data for that object. This is a bit of, this is a minus 18 declination, but ZTF was still able to provide some observations for it. Then Atlas is another survey, and we, as I said, we grab the data automatically in our system. So there is more, of course, right? From Atlas we see, but the data quality is as it is, and the filters are not very standard. And here comes the observations collected with the telescope network. So you see this is extremely dense, and we managed to reach very far to the peak here. Actually, this is the place where the object went behind the sun, unfortunately. So we couldn't help it. But you see with this data, we were able to detect some very tiny, small features of the light curve, like this bump and this bump here. We covered this peak very densely. These are crucial elements of the light curve we need in solving microlensing events. And I guess this applies to many other science cases. This is the G-band observations. So a word about archives. So we are automatically harvest the archival time domain data for given coordinates. So this is just one caveat. You need to know the coordinates of your object pretty well, right? Let's say down to 1 arcsecond, let's say. If you have a vague idea where your target is, then we are working on it, and hopefully in next versions of BHTOM we will be able to we are able to process the data, but the system is target oriented, right? This is how the original TOMs were built. So this is just to keep in mind. So if you know your target down to 1 arcsecond, then you can add it, and then automatically you get all these archives downloaded for you. There is still a long list of time domain data we hope to add. There is even Harvard photographic plates been scanned. It's called DASH. So I've been thinking about adding this as well. For some objects, you can get 100-year-old observation, time domain observations. So that will appear sometime soon. Yeah, so here just to show you some examples of how the archives work, just archival data with some follow-up observations. And more examples. This is a famous blazar and some Asian flare from TNS. Just to show a couple of publications we published. So you see the long list of authors. This is what I wanted to emphasize here. We encourage the authors of the scientific observation publications to include all the observers in the author list. This is very encouraging for people doing observations. Sometimes these are just operators of the telescopes. You know how it is essentially. You want to appear, you want your work to be acknowledged, and adding a person with a name and affiliation to a paper doesn't cost much, but sometimes it's very crucial for all these small telescopes that they can show. They can go actually to their funding agencies. Look, our telescope has been contributing to this number of papers. Excuse me. And hence they can get some funding, local funding. This happened many times already. We've been providing letters of reference and also list of publications for some small observatories, and then they were able to secure some additional funding for their operation. So this is the way we operate. Just a word about BHTOM for gravitational waves. We haven't done this yet because there has been no candidates, reasonable candidates so far, but at least recently. But we are there. We are capable of observing the candidates. I want to emphasize this. You need to know your candidate where it is, and then we can respond if you find your candidates. If you give us 10 candidates best for optical counterpart and throw it into the system, then we can confirm it very quickly and give you the data back. You don't have to process the data, you will get the observations immediately. And also we can roll out some candidates based on historical data. And of course we do the automated processing. And we observe the galactic plane. Just to emphasize this, not everyone does. There is a newsletter, BHTOM newsletter, an open Google group. You can sign in and see what's going on every week, what kind of targets are of interest now. So if you're planning your observation on a weekly basis, then you can read that list essentially and see what kind of targets are there of interest. Of course, you can generate this kind of list yourself. I also send a targeted mailing list per telescope so that this is a list tuned for that particular observatory, its location, its magnitude limit, and air mass, and so on. But of course, you can query our table every time you are at your telescope. You see you have 1 hour gap in your scheduled observations, and you don't know what to do with your telescope. You just run your script. You get a list of targets which are now of interest and are now visible, and you can plug it into your scheduler and provide the data for the system. Okay, speaking about plans for the future. So this is a more elaborate schema of the system. So we are working with LCO to spread to talk with other TOMs as well, so that BHTOM is one of many multiple TOMs which are installed at different places globally. This will also help speed up a little bit of data processing. We do process a lot of data and we can process more, but of course, if you would like to process all your archival observations, then you would essentially just block our processing pipeline at the moment. And so that's why we're trying to distribute that a little bit more, so that there are like copies of our processing system in multiple nodes, like LCO node or South African node or some other nodes, wherever there is more data coming from. And then there is a common archival database, and the data is shared between the TOMs. And of course, we're working on the unified communication with the telescopes using the EON. So summarizing, so BHTOM is a global network of optical telescopes for time domain observations. It provides long-term multi-wavelength photometry for your target. It accesses to many optical and radio time domain archives. And in terms of plans, we've had some conversations already at the LSST level that BHTOM could be the place to coordinate all the in-kind follow-up resources. So there's many telescopes who offered the follow-up capabilities as in form of in-kind contributions from outside of the US. And BHTOM could be a good place to gather them all and control it from one place. Of course, we want to move to multi-messenger targets like GW and neutrinos. We hope to also be able to process solar system objects. This is on our agenda, that essentially we can build light curves of moving objects. And then, of course, more archives, multi-messenger, X-ray, gamma, radio. So we are working on it. And if you have any other ideas, then give me a shout. And last slide about the European Astronomical Society of Small Telescopes, something I mentioned in my title. As I said, this is the very first time I'm announcing this publicly. So this is a foundation we are now establishing, and the main goals are listed here. So we will be advancing citizen science with the use of small telescopes. Essentially, small telescopes can be involved in citizen science using BHTOM as the core tool for that. We'll be doing outreach activities, local and global activities. We'll be connecting astronomers, professionals, and amateur Of course, expanding the telescope network for science. Also, we'll be focusing on enhancing telescope technology, how to help the small telescopes to fight the weather, to fight the data processing. So all this is in our mind. Protecting dark skies. I don't have to say more about this, I guess. And of course, build international partnerships in astronomy. Essentially, my last slides here. So we've been running the workshops I mentioned from the very beginning. Actually, we started in 2010, way before Gaia was launched in Cambridge. And we've been having these workshops every single year, with one being online, and everything is recorded on this webpage. And I would like to invite you to the workshop we are about to announce. This is going to be 16th Gaia alerts and the first ACME time domain workshop. ACME is the European grant we now are funded with. So this is going to happen in IAC in Tenerife at the end of September, beginning of October. And I'll stop here, leaving the contact details to me. Thank you.
Thank you so much for this for your presentation. This is amazing work and really also an example of what collaboration can achieve. So thank you so much, and I hope a lot of people get involved.